The conflict predictions of the Global Early Warning Tool are generated through the use of supervised machine learning. Because there is little consensus on which factors cause conflict, machine learning enables us to exploit correlations without directly linking conflict to its cause. The model identifies patterns in the historical data and uses these patterns to predict conflict given current conditions. The Global Early Warning Tool uses a random forest model for this analysis. The random forest model works by using decision trees. In a decision tree, a random subset of variables is input, and the tree creates branches to separate the data based on differences between variables and how well they align with conflict events. Within the model, the decision trees can grow a large number of branches as they would like until the prediction or a leaf of the tree is selected. The random forest works by using a forest of decision trees to generate the conflict forecast. By using a large number of decision trees, the machine learning enables the model to incorporate datasets that are dissimilar and reduce variance of conflict predictions. This gives the model flexibility in the range of input datasets and enables the confidence in the forecast to be assessed by analyzing the predictions generated by multiple trees. A range of input variables was considered for the random forest model. Initially, more than 200 socioeconomic and environmental variables were assessed. These variables were selected based on a literature review of factors that contribute to conflict. They can broadly be lumped into the United Nations Development Programme's Human Security Framework under the categories of community, conflict, economy, food, governance, and water, with plans for future expansion. Notably, water and environmental variables are only one part of the analysis, as we understand that multiple factors influence the likelihood of conflict and do not want to limit these relationships in the model. These data sets were then compared against historical conflict data where 10 or more fatalities occurred per year from the armed conflict location and event data dataset. The input variables were then narrowed to less than 20 predictor variables based on recursive feature elimination. Recursive feature elimination identified which of the input variables were most correlated with the historical conflict data so that we could use a limited set of the highest performing variables to generate conflict forecasts based on current and future datasets. The variables were narrowed down to fewer predictor variables for several reasons. First, fewer variables support the interpretation of the model as there are fewer complicating factors. Second, too much input data can enable errors in the model because the model becomes overfitted with historical conditions instead of looking for broader patterns. Through the narrowing of input variables, the model does not lose as much accuracy. Although the predictor variables are not necessarily the causes of conflict, they do indicate factors that likely contribute to conflict. Of the 17 best predictor variables, 6 relate to water. These patterns indicate that water likely contributes to conflict or correlates strongly with certain causal factors that can affect water systems and conflict dynamics, such as bad governance, conflict history, overpopulation, or a specific climate. Further, analysis also demonstrated that water-related predictor variables had a more significant impact when conflict was defined below 10 fatalities per year, especially with respect to emerging conflicts. These patterns cannot link water as a cause of conflict, but indicate a strong likelihood that water is part of the process and merits further analysis to understand possible causal relationships. The connections between water and conflict are studied in greater detail in the next regional-based phase of the Water, Peace, and Security Framework. While looking at applying the model, it's important to understand how its construction influences the results. The process of comparing historical input data to historical conflict events is training the model. This provides the structure that a model will use when the model ingests current input data to compute future conflict predictions. In determining which results to prioritize, the model was trained to predict the existence of conflict. As a result, the model conservatively predicts conflict, leading to overprediction. However, this process also enables users to support interventions to mitigate potential fatalities. The model is updated on a quarterly basis and provides one-year forecasts, which supports timely action and rings an alarm bell for others to respond to. In their responses, individuals can make use of the water, peace, and security integrated approach.